Hello, physics students. This lesson is on section 2.2 from your textbook, Introduction to Acceleration. So we've been talking about velocity and how it is displacement over time. Now we're going to talk about how, as velocity is not constant, acceleration can occur. So you have a notes page. Go ahead and fill that out as I go through this lesson. And if you need to, make sure to pause frequently to make sure that you're understanding everything, and you can always come back to it later. Definition of acceleration: the rate of change of velocity in a given time interval. We perceive the relative acceleration. For example, if a bus stops slowly, the acceleration is much less than if the bus driver must slam on his brakes. And of course, if you're thinking about that, you're thinking, well, it doesn't accelerate, because usually we think of acceleration as speeding up. But actually, acceleration has both a magnitude, which is a number, that's the part that got larger, and a direction. So obviously, even though it's a faster acceleration or the number's bigger as an acceleration, the direction is what you're thinking, nah, that didn't really make sense. The direction is determined by the direction of travel as well as whether the object is slowing down, speeding up, maintaining constant velocity, or resting. Speedy Gonzalez here doesn't get it. He says, I'm going faster. What do you mean my acceleration is negative? But if you remember, he's going to the left, and left usually represents west, and west is a negative velocity. Therefore, if he's going faster and he's going negative, then really his acceleration is negative. This chart is designed to look at if acceleration is positive or negative. So first we have to consider, does the original velocity start as positive or negative? Remember, north and east are positive and south and west are negative. The object is, this column, is like, is it going faster? Is it going slower? Is it stopping? What's going on with the object right now? And then we'll determine if acceleration is positive or negative, or zero. So we start off with a positive velocity, so that means it's going north, east, or forward, and it's speeding up. Well, if it's already positive and it's going faster, obviously acceleration is going to be positive. But what if it's going in the positive velocity to start off with and it's slowing down? Well, hopefully you can reason that if it's slowing down, acceleration is going to be negative. Now, if the velocity doesn't change or it's constant and we start off positive, now our acceleration is zero. So all three of these started in a positive direction, but if it sped up, it had a positive acceleration or a positive change in velocity. If it slowed down, it had a negative change in velocity. And if it didn't change velocity, the acceleration was zero. Now let's look at if we started in a negative direction. This is the one that might be a little counterintuitive. So if we're starting in a negative direction, southwest or backward, and speeding up, what do you think acceleration would be? Well, if you're speeding up on the negative, your acceleration will be negative. But what if you start off negative and you slow down? Now you're actually going negative still, but you're not going as fast. So your acceleration is actually positive. What if you're at constant velocity? Well, hopefully it makes good sense that anytime you're at constant velocity, your acceleration is zero. So this is the opposite of above. Whereas constant velocity is always going to give you an acceleration of zero, the speeding up and slowing down are opposites. So if you speed up in the positive direction, you have positive acceleration. Speeding up in the negative direction gives you negative acceleration. And if you are slowing down, positive direction is negative acceleration, and slowing down in the negative direction is positive acceleration. Take some time to think through that. Make sure that it makes sense. Okay, what if you just started at no velocity? So velocity is 0, you're not moving, and you speed up toward the north, the east, or forward. Well, you're going positive direction, so your acceleration is positive. What if you are not moving and you start moving backwards or to the south or to the west? Now you're accelerating negatively because you're going in a negative direction. What if you just stay the same? So again, we have a constant velocity, this time velocity being nothing, 0 acceleration. We'll spend some more time talking about this in class tomorrow, but just try to make sure that you're getting a handle on what we're talking about as far as positives and negatives here. Now we're going to move on to the math. Average acceleration may be calculated as a ratio of the change in velocity to the change in time. So A average acceleration, is equal to delta V over delta T. Remember that delta symbol just means change in, and delta V is the same as taking V final minus V initial over T final minus T initial for delta T. The unit for acceleration is meters per second squared. This is a derived unit that comes from the unit for velocity over the unit for time. So if we say meters per second, and then we divide that unit by seconds, that's how we get meters per second squared. Of course, that's if we're using meters in seconds. It might be kilometers per hour squared in several of your problems, or it could even be meters per hour squared if something was going very, very slowly. Let's look at a few examples. A shuttle bus slows down with an average acceleration of negative 1.8 meters per second squared. How long does it take the bus to slow from 9 meters per second to a complete stop? Well, the first thing I'm going to suggest is that we go through the problem and we underline any information that it's given us and try to label it. You might want to pause here and try that on your own before letting the video advance. I hope you underlined what I did. I have negative 1.8 meters per second squared. That's an acceleration. I have a delta t equals question mark because it's asking how long. And delta v is the final minus the initial velocity. So it says it comes to a complete stop, so the final velocity is 0 minus the initial velocity, which is 9, so 0 minus 9 is negative 9 meters per second. It's important that I don't just say 9 meters per second because I have to find the change in velocity. And again, I'm going to take my final minus my initial, so 0 minus 9 is how I get that. Now, when I want to find the delta t, I can rearrange my equation. I know that average acceleration is equal to delta v over delta t. If I multiply both sides by delta t, I get delta t times a average is equal to delta v. And to get delta t by itself, I would divide both sides by a average, and I get delta t equals delta v over a average. So I'm using the isolation of the variable, in this case delta t, because that's what it asked me to solve for in the problem. Now I'm going to go ahead and put in my numbers. So I know that delta t is equal to delta v over a average. That's negative 9 meters per second over negative 1.8 meters per second squared. When that gets divided out, the answer is 5 seconds. Go ahead and try it for yourself. Example 2. A car accelerates from rest to a speed of 36 kilometers per hour in 20 seconds. What is the acceleration of the car in meters per second squared? Again, I would pause here and go ahead and see if you can figure out the problem without my help first, and then you can come back and see me work it out. I said from rest to a speed of 36 kilometers per hour is a delta V of 36. This time it starts at rest, so I take the final 36 minus the 0, and that's positive 36 kilometers per hour. 20 seconds is given to me as delta T, and then it asks for the acceleration. So I know my equation is acceleration is equal to delta V over delta T. I have delta V in kilometers per hour. I do have a delta T, however, it's in seconds, and I know that I have to make sure that my units match up. So when I need to do a unit conversion, I usually go back to dimensional analysis. So I want to get the number of hours down here. I have to use 20 seconds to be able to do that. So we've done this many times. 20 seconds, 1 minute for 60 seconds, 1 hour for 60 minutes. That gives me 0.006 hours. Now I have the proper unit to finish what I started. So now when I go back here, I can plug in 0.006 hours on the bottom of the 36 kilometers per hour, divide that out, that's 6,000 kilometers per hour squared. Now, some of you might have been tempted to use dimensional analysis the whole way. Can you figure out why you can't do that here? These tricky units make dimensional analysis less practical. So up here in red, I already showed you how I went from 20 seconds to 0.006 hours. Now if I wanted to go with that and then use 36 kilometers per hour as another conversion factor, the problem with doing that is I'd cancel out hours and my unit would be kilometers. That's not my desired unit. I wanted kilometers per hour squared because I was solving for acceleration. If I was solving for kilometers, it would have been fine, but that's not what I'm solving for. So that's why you really do need to isolate the variable and solve. On these problems, you only want to use dimensional analysis for unit conversions. Okay, so you can see here, if I canceled out hours, I just end up with kilometers. Okay, try example 3. It's a little more tricky. See what you can figure out without my help, and then watch me do it. Starting with a constant velocity of 50 kilometers per hour. That's my initial velocity. A car accelerates for 32 seconds. That's my delta T. At an acceleration of 0.5 meters per second squared. That's my average acceleration. What is the velocity of the car at the end of the period? Oh, so now I don't have VF. So I have to find VF. What do I know about VF? By the way, that last 32 seconds is just a repeat. It was already given to me as delta T. So what do I know about VF? I know that delta V is equal to VF minus VI. Therefore, I know VF must be equal to delta V plus VI, because I can just rearrange that equation by adding VI to both sides. But I don't have delta V. I can find delta V, and then I can come back to this. So we're going to actually do a little side problem, and we're going to find delta V. Delta V equals A average times delta T. That's just coming from my original equation that we started with today. If A average equals delta V over delta T, then delta V must equal A average times delta T. Okay, I can plug that in. 0.5 meters per second squared times 32 seconds, that's 16 meters per second. Now I have delta V. So we said that VF was going to be equal to delta V plus VI. So 16 meters per second plus 50 kilometers per hour. Easy. right? No. Why is this not going to work? You probably recognize that you can't add meters per second with kilometers per hour. Those are not like units. So I've got to change one of those so that I can have two units that are more alike. I'm going to go ahead and change meters per second. This is some tricky dimensional analysis because not only do I want to change meters to kilometers, I also want to change seconds to hours, and I'm actually starting with a conversion factor. Most of the time when we use dimensional analysis, we want to start with something that only has one unit, but this actually has the two units together, and usually we would use that as a conversion factor. Okay, let's focus on meters to kilometers first. If I put 1 kilometer over 1,000 meters, I can cancel out meters. Now I have kilometers on top and seconds on bottom. So I'm just going to keep going, and I'm going to get rid of seconds, and I'm going to get all the way to hours. So if I put 60 seconds on top, I can go back and cancel out seconds, and I'm going to put 1 minute on the bottom, but I don't want minutes, I want hours, so I've got to add another conversion factor, 60 minutes for every 1 hour. Now I've canceled out everything except for kilometers on top and hours on bottom. So I've got what I want, kilometers per hour. That's 57.6. Now I'm ready to finish this problem. It's been a long one. I know you might have had to use extra paper. That's okay. Hopefully you're understanding the procedure though. Okay, so now that we have it in kilometers per hour, we're ready to finish the problem. So remember, we have final velocity is equal to change in velocity plus initial velocity. Final velocity in kilometers per hour is 57.6 plus our initial velocity is 50. When we add those together, we get 107.6 kilometers per hour. And that is your final answer. You will have one in your homework that will be similar to that. So your homework is to complete page 45, numbers 1 to 5. No excuses. I want it done tomorrow in class, and then you can ask as many questions as you want, but I want to see that you've at least tried all of the problems. Have a great day.